part of the class. Okay, it have started. Okay, so well, today we have the last class of high performance architecture together. You will have more classes, but with other teachers. As I told you at the beginning of the subject, I was going to be in charge of just talking to you about chapter 1 and chapter 2. And then in chapter 3, that is about cache coherence, you are going to have another teacher from Coruña, whose name is Juan Torino. Okay, so in chapter 1, what we did at the beginning was to establish which are the main trends of computer architecture nowadays. Okay, and we talk about the idea of power consumption that was increasing as a consequence of increasing also the frequency of the processor. Also, the design of each processor was overly complicated. Okay, so, okay, we are going to wait a few minutes because some students are arriving now. Okay, so we were talking about the current trends in computer architecture, such as power consumption, multi-core computers, etc. And then we made a small review of basic contents or basic knowledge about computer architecture. It is something that if you study computer architecture or computer science in the past, probably it was just a review of that knowledge that you already acquired. In chapter 2, and this is the chapter that we are covering right now, we were going to talk about several topics, but the main topic that unifies all of them is to talk about parallelism inside the processor. Okay, how the processor has mechanisms in order to exploit parallelism inside of it. Okay, and this is what we started last class. At the beginning of this chapter, we covered the different forms of parallelism, the different forms of parallel computer. Okay, and now we are going to talk today about two different topics. The first is advanced instruction level parallelism. We talked already about instruction level parallelism, that is a very basic ability of modern processors that is based on the usage of pipelines. Okay, but now we are going to improve this with new techniques, okay, that are available in all modern processors. And after that, we are going to talk about thread level parallelism, the ability that modern processors have to execute several threads at the same time, okay? And then in a second part of today's class, we are going to talk about the layout of multi-core processors, okay? How they are internally organized. Okay, but first of all, let's talk about instruction level parallelism and thread level parallelism. Okay, so in the last chapter, when we review basic knowledge of computer architecture, we talk about the concept of pipelining. Pipelining is the idea of applying the concepts of a production line or a factory line to the execution of instructions inside a processor. The purpose of this was okay, let me check because Okay, the purpose of this was to be able to execute several instructions at the same time, but in an overlap manner. Okay, so the idea is that we were going to divide the execution of any instruction in a processor in several stages. So different stages require or imply the usage of different hardware. And the idea is that we were executing several instructions at the same time in a fully overlapped manner. Okay, so now what we are going to talk about is how to increase instruction level parallelism. When we talk about pipeline for the first time, we saw a toy sample processor where the execution of one instruction involved 5 stages. Okay, and these stages were instruction fetch, instruction decoding, execution of the instruction itself, memory, and write back. Okay, but I already told you that this is not real. Okay, in model processor, we have many more different stages in a pipeline, and some of them are optional and others are mandatory. Okay, so which is the real number? The real number is around 20. Okay, so you are going to find processors which are simpler, probably with 15 stages or something like that, and others that are more complicated, and they are going to have like 20 stages or something like that. So this idea of creating more stages during the execution of instruction is called deepening the pipeline, okay, creating a longer pipeline, and is also referred as super pipelining. Okay, so as we are doing a more atomic work per stage, okay, this is going to allow us to shorten the clock cycle, the duration of the clock cycle. Okay, and if we shorten the duration of a clock cycle, what we are doing is increasing the frequency of the processor. And remember that this was one of the main motivations for the improvement of the processor until the beginning of the 21st century. Okay, so obviously this is an idea that has been widely applied in the design of model processors. If we are able, or if we divide the execution of one instruction in 20 stages, at maximum we can have, at least from a theoretical point of view, 20 instructions being executed at the same time. Okay. Another idea that can improve the pipelining is what we call multiple issue. Okay, and we will see that there are several examples of this. The idea of multiple issue is when you fetch an instruction to be executed. So even in a pipeline processor, we are supposed to issue a new instruction every cycle, okay, not several of them. That's the idea of pipelining. But we can extend or complicate this idea just allowing to issue several instructions in the same cycle. Okay, and obviously this is going to increase the amount of instruction level parallelism. In order to do this, one of the most straightforward ways to do so is to replicate the pipeline. Okay, like several copies of the pipeline. But obviously, if we replicate the full pipeline, what we are doing clearly is to create a new core. Okay, but beyond this idea, we have also the idea to replicate it just partially. Some stages are replicated, other stages are not. Okay, so just some of them. We are going to replicate some functional units. So for instance, we can be able to execute several multiplications at the same time, or several divisions, or something like that, okay? Okay, so the overall target is to start multiple instructions per clock cycle. And when we talk about pipelining, we mentioned that if this works very well without any delay, the CPI that was going to be achieved is 1, okay? Let's recall that the concept of CPI is the number of cycles required to execute each instruction, okay? So if the pipeline works like a charm, we are supposed to finish a new instruction every cycle. So our best CPI is going to be 1, okay, in the best case scenario. But obviously, if we are able to execute several instructions at the same time, or issue several instructions at the same time, we are able, theoretically, to achieve a CPI that can be clearly smaller than 1. And actually, when in HPC tools, those that have this subject use these profiling analysis tools, you will find that sometimes the CPI of a computer during the execution of a code is smaller than 1, okay? And this can surprise you at first, and what is really going on is that they have multiple issues. Okay, so this is a rough calculation about what happens in a computer with 4-way multiple issue. 4-way multiple issue means that the computer is able to start the execution of 4 new instructions every cycle. Well, theoretically, you are able to achieve a CPI of as small as 0.25. Okay, here, the smaller the better, okay, because we are clearly below the value of 1. And the IPC, that is the counterpart metric of CPI, instructions per cycle, is about 4, or can be 4 maximum, okay? But obviously, as we already mentioned, when we talk about pipelining in general, the dependencies between the different instructions are going to avoid that we achieve this theoretical ideal performance. Okay, so how do we implement this? Well, the first thing that it can be made differently is who chooses the instructions that are going to be issued at the same time, okay? Because obviously, issue 4 instructions or 2 instructions or whatever number of instructions at the same time implies that you have to make a dependency analysis, because if there is a dependency between a pair of instructions, they cannot be issued at the same time, okay? So if this analysis is done by the compiler, we said that this is going to happen at compile time, and this is what we call static multiple issue. Okay, this is the approach that we follow. And this is implemented in a kind of machines which are called very long instruction word. Okay, this is the acronym of very long instruction word machines. The idea is that the processor is going to create like packages of up to 2, 3, 4, or whatever number of instructions to be issued at the same time, okay? And it's up to the processor to make the analysis to avoid hazards. This is not very frequent, okay? It was frequent at the beginning of the 21st century, but today the most common scenario is that the issue or the decision of which group of instructions are going to be issued at the same time is done by the processor at runtime. This is what we call dynamic multiple issue, on opposite to static, okay, because it happens dynamically during the execution of the code, and the kind of machines that have this ability and that are basically most of the modern processors are called superscalar processors, okay? The idea is that at runtime, during the execution of the code, the CPU, the processor, is going to examine a window of the next instruction to be executed, okay? And it decides which of them can be executed in parallel, which of them can be issued at the same time, okay? If necessary, prior to this, the compiler can help by reordering instructions. So sometimes the compiler can help because it changes the code to create multiple issue opportunities for the processor, okay? But this is not something that happens all the time. And the CPU is going to resolve hazards using advanced techniques during runtime. And you will see that this is going to complicate a lot the design of the processor. Okay, so let's talk a little deeper on static multiple issue. On static multiple issue, the compiler, and here is going to be very relevant that the compiler is aware of the architecture, has to create issue packets, which are packets of a given number of instructions, the one that can be issued by the processor at the same time, okay, that are going to be decided to be executed or issued concurrently, okay? When we think about an issue packet, we have to think about a very long instruction, okay, where we have something like an addition with its operands, a subtraction with its corresponding operands, and so on, okay? So this is going to create like very long instructions, and this is the origin of the name very long instruction word, okay? Because instead of having single atomic instructions like we have in non-superscalar processors, we are going to have super instructions composed of several simpler instructions that have to be issued at the same time. Okay, and this is a view or an illustration of just the IF instruction fetch and ID instruction decode stages of one of these very long instruction code processors. Okay, so what you see here is that from the instruction cache, we are going to get the codification of one of these instructions. But in a normal or regular instruction, before that, we have always like an operand and then, an operation code, and then several operands that were used by the instructions. But now we have like several of them put together, okay? Each instruction is going to require different values or different registers from the register file, and you can see that the hardware to do so is separated, is replicated, because this has to happen concurrently, okay? Okay, the other, in the case of, we are still in static multiple issue, the scheduling of the instructions, the creation of these very long instructions is up to the compiler. The compiler has to make some kind of static analysis in order to first reorder the instructions, to put together those instructions that are not dependent okay? And then with them is going to create issue packets, okay? The idea is that there must not be dependencies within a packet, okay? Because if there is, then this is going to be a problem because the semantics of the code can change. At some cases, you are not going to have an enough number, a sufficient number of instructions to be packaged together. In that case, you are going to put or to complete the packet with no operations, okay, with instructions that basically do nothing. This is an underutilization of the resources, but this is perfectly fine, okay, and it's actually happening all the time in this kind of computers. Okay, so this is a very simple example of a computer that has static dual issue. So this means that a very long instruction is composed of just 2 atomic instructions, okay, put together. And there is an important restriction for this, and is that... Aquí tienes un resultado de la web. Okay, shut up. And there is an important restriction here, and is that one instruction can be a branch instruction or an arithmetic logic instruction, and the other one has to be a memory load or store instructions. Why is that? Because if you issue 2 instructions to be executed fully in parallel, to be issued at the same time, at some point, they can require the same hardware. And if that happens, this is going to ruin the concurrently execution of these instructions. So this architecture assures this, just telling you that you have to create packages of one instruction of this kind and another instruction of this kind. Okay, this is a quite strong situation. Okay, so this will be one package, and as you can see, you can start one of these instructions and one of these other instructions at the same time, and they go through all the pipeline stages from the beginning to the end concurrently without any delay. Then you can start 2 more, and then 2 more, and so on. Okay, so in this case, theoretically, you can achieve a CPI of 1 divided by 2. Okay, not here in this example, but if this happens ideally for a long period, this is going to be the value or the CPI to which is going to tend. Okay, so the other approach, and this is the most usual approach that we have nowadays, is that instead of doing this composition of instructions at compile time by the compiler, this is going to be done dynamically, and that's the source of the name dynamic multiple issue, by the processor. And the kind of processors that we have nowadays are called superscalar, okay, superscalar because of this. Actually, after this first half of the class, I put several links in the chat, okay, of the meeting. And these 3 links are modern architectures. This is the Zen2. This is one of the most modern architectures from AMD. That is one of the most important chip manufacturers, okay? And you can see that this is a superscalar, okay? So this is what is being implemented right now. This is the Ice Lake architecture from Intel. Most desktop computers that are sold nowadays have this architecture. And you can see that this is superscalar, okay? And this is the Power 9, okay? That is one of the most recent processor or architectures, in this case, from IBM, okay, another major manufacturer, and you can see again that this is superscalar, okay? So the question is, what does this mean? So if we have the ability to execute several instructions at the same time, and the packaging or the selection of this instruction is done dynamically by the compiler at runtime, this is the definition of a superscalar processor, okay? And this is available in all modern processors nowadays. Okay, so the idea is that at runtime, the processor have a lot of mechanisms to choose which instructions are safe to be executed at the same time, because they can be structurally done concurrently by the compiler, and also it checks that there are not data hazards among them, okay? That one of the instructions is not generating a value that is required by another instruction, because obviously in that case this is going to change the semantics of the code. In other situations where this can be solved by any mechanism, like for instance register renaming, okay, this is going to be done by the compiler automatically. Okay, so the compiler still can play a role just reordering the instructions and putting together all the instructions that can be executed at the same time, okay? Just to facilitate the work of the processor, okay? So it's not an important role like it had in the previous approach, but it's still a good role. Okay, so this is an overview, a simplified overview of the pipeline of a two-way superscalar processor. So two-way means that we are going to be able to issue two instructions at the same time. So you can see that here the instruction fetch and the instruction decode stages have to be duplicated, because if not, this cannot happen concurrently. However, when you arrive to the execution stage, you can see that the hardware is not replicated, at least in this example. So this means that, for instance, maybe you are not able to execute two multiplications at the same time, okay, or two additions at the same time, because this hardware is not replicated, okay? So it's up to the processor to decide which instructions can be executed concurrently depending on the hardware that has available, okay? So obviously this is a very simple example, okay? The hardware is quite simple, just as an example to you, but this will be a restriction. And also, something else happens in the write back stage. This stage is where you are going to store the result of the computation. If you make an addition, you are going to store the result of the addition in a register. If you make a load operation, you are going to load data in a register. And you need this hardware replicated in order to be able to do this concurrently, okay? Because if not, that's not possible. Okay, so something that is implied by dynamic scheduling is that sometimes the CPU is going to decide to execute the instructions out of order, okay? Do you remember the concept of out of order? Out of order means that you don't have to start the execution of the instruction in the order in which they are written in the program, okay? Because this way you can reschedule the execution of the different instructions, okay? Regarding finalization, okay? And this is when the instruction finishes and commits each stage to registers or to memory or whatever. The finalization can be guaranteed to be in order because this is a safer policy, okay? You can start out of order, but the hardware is going to make sure that at the end, the finish happens in order, because this is going to guarantee part of the semantics of the code. But there is also many examples of processors that can handle situations where the execution, the complexion of the instructions happens out of order. So obviously this is going to complicate further the design of the processor. Okay? Okay, so this is just a tiny example of an out of order execution. Think that you have a two-way dynamic multiple issue processor, okay? And this processor examines the code to know which other instructions can be started or issued at the same time that the load operation, okay? So the ADU, this instruction, is not a good candidate. Why is that? Because it has a hazard, okay? A hazard because this instruction is going to load a value from memory that is going to be used by this other instruction, okay? So the next candidate is the subtraction, okay? And the subtraction doesn't have any dependencies with respect to the load operation, so it can be executed concurrently at the same time. And this is an example of out of order execution that happens because of dynamically multiple issue processor. Okay, this is the idea. Okay, so this is an overview of a deeper overview of the dynamically scheduled CPU. There is something that we don't mention before. We are not going to enter into detail of what is this and how it works, but basically, when you work this way, you are going to have like many pending operands, okay? And in order to manage this situation, you need a piece of hardware that is called reservation station, okay? And this is required because of the out of order execution. And what you can see is that you have many of them, okay? Because when you execute instructions out of order, you are going to have to establish association between like producers and consumers, instructions that are going to be generating results that are going to be consumed by other instructions. Okay, so another important piece of engineering that is required to make this work is speculation, okay? Speculation is a normal word, regular word in the dictionary. That means that you try to guess what is happening in the future. And it's crucial for the processor for achieving a good performance that sometimes the processor speculates. And when this happens, this means that you are going to start an instruction as soon as possible, okay? And abstractly, you have to check when the speculation is finished and after the event happens, if you were right or not. If you were right, the speculation was okay, was correct, and then you can go on with the execution of that instruction that you started speculatively, okay? If you were not right, then you have to roll back, to rewind the state of the processor until a previous stage, because the changes that you made to the state of the processor were not right, okay? Because you speculated, you failed in your prediction, whatever this prediction was, okay? And then you have to rewind the changes that you made to the processor. This speculation is going to be useful not just in dynamic multiple issue, that is the thing that we are talking about right now, but also in the static one. So the question here, because speculation is an abstract concept, is on which kind of things we have to speculate. One thing, we already know it from chapter 1, and is a branch outcome, okay? When you arrive to a branch instruction in a code, you have several options. The first one is to wait until you know what happens with the branch, okay? Until we say the branch is decided. Because depending on the outcome of the branch, you are going to continue with the execution of the next instruction of the code, or you are going to jump somewhere else, okay? So waiting is not an option, okay? You are going to discover that computer architectures are very obsessive people, okay? Because they are paid for this. And they don't want to lose these cycles. So what they do to avoid this is to try to guess which is going to be the outcome of the branch, okay? And actually, if you check these three documents with these three state-of-the-art architectures, something that is very described in detail in these documents is the branch predictor, okay? Because this is a key component of the performance of a computer architecture, okay? Okay, so this is something important. So if you discover that you were right about the branch prediction, then you can go on with the execution of the instruction. If not, obviously you have to roll back those instructions that you started speculatively, okay? Another thing where you can speculate is on a load operation. Normally, when you load something from memory, it's very hard to know if this memory position is going to be updated or not by a previous store operation, okay? So you have like many instructions in your code. You have loads and stores everywhere because they are moving information from or to the memory system. So if you want to make a load operation safely, you have to wait until all the previous store instructions are completed. Because if not, there is not way, or there is not an easy way, to know if any of them are going to update that position, okay? So this is a problem for performance because when you are trying to issue like many instructions at the same time, all these restrictions, like this one, you cannot make a load operation until all the previous stores are completed, okay? You want to get rid of this restriction. So the solution for this is just to speculate, to think, okay, I'm going to guess that this position is not going to be updated. Then I'm going to make the load operation. But if finally you discover that you were wrong, you have to roll back that, to rewind that situation and make the load of the appropriate value. Okay. This is what I told you before. Okay, so this idea of speculation can be done also in the compiler, but with one specification, and is that the rollback code has to be included explicitly by the compiler, okay? Because obviously, if this is done by the compiler, the hardware cannot be involved, okay? And we cannot assume that there will be a rollback, a checking and a rollback mechanism from the side of the hardware, okay? So the FISA instructions have to be included by the compiler itself. Okay, so this is the comparison of two processors. They have, I believe, like 10 years or something like that. And you can see that this is a mobile one, pretty old, okay? And this is a desktop or server one, okay? And you can notice the difference between them. One of them, and this is very obvious, is power consumption. If you plug the Intel i7 of your desktop computer to the battery of your smartphone, it's going to drain it in minutes, okay? So obviously, the thermal design power that we talked about at the beginning of this subject has to be much smaller. One of the reasons for this is the complexity of the hardware. For instance, the clock frequency is usually smaller in mobile processor because, as you know, the higher the frequency, the more power is going to be consumed, okay? Because the switching of the transistors is happening more frequently. Also, one of them has a single core, although this is not the norm nowadays, and the other has 4, okay? One of them has support for floating point operations, the other doesn't. The length of the pipeline is more or less the same, 14 stages, okay? And what is important to us is how is the execution of instructions. In the mobile processor, the execution is static in order because this simplifies hardware, and in the other, we have like the full package of characteristics: dynamic, out of order, execution with speculation, okay? So you can see that this kind of aggressive improvement of the performance of the processor is not good for any platform because it requires transistors, it complicates the design of the processor, and most importantly, it consumes a lot of power, okay? Obviously, you trade power by performance. Okay, at the end you find the characteristics of the cache memories, okay, but they are not very relevant. One of them have 2 levels of cache, and the other have 3 levels. Okay, so the first processor, the mobile one, this is an overview, a simplified overview of the pipeline of the processor. Okay, so you find here instruction fetch stage, instruction decode. Remember that we have a pipeline with 14 stages of execution. And then in the part of the execution memory stages, we find like many different paths that can be followed by different instructions. Okay? And this is the pipeline of an Intel Core i7. okay? That, as you can see, this is much more complicated. And this complicated design is because we need mechanisms, in part, to be able to make dynamic out-of-order execution of instructions with speculation. So the cause of this is power, but because the hardware is much more complicated, okay? And also we have lots of replication, okay, of different hardware that is replicated to enable the parallel or the concurrent execution of instructions of the same kind, but obviously this is the real situation in desktop computers. In any of these three articles, okay, you are going to find an overview of the pipeline of a single core in one of these architectures. This is the pipeline of the Zen 2 architecture, which is composed of 19 stages, okay? In Ice Lake is also quite complicated. So this is like between 14 and 19 stages because some of them are optional. Okay, and I don't know if, yes, they have the same information, but sparse between different illustrations. Okay, and for the Power 9, I believe that you have, yes, you have here the same kind of outline illustration about the pipeline. Okay, so so far we have talking about more aggressive ways to extract instruction level parallelism. Okay, and when we try to issue several instructions at the same time, one of our main enemies are hazards that we already know from our computer architecture review. We have structural hazards, data hazards, and control hazards. Okay? Okay, something that can be done for exposing instruction level parallelism is to apply some techniques to the source code or to the machine code. So this can be done by you as a programmer, and you can try this yourself, okay? Or this can be done by the compiler itself. Actually, if you don't do it, probably the compiler is going to do it by you, okay, instead of you. So this is a code, okay, where I'm adding a value x to each element of an array x, okay? So these are the latencies of the different instructions that are going to be involved in this code when it's translated into machine code. And this could be a possible implementation of this code, okay? So we have a loop, and at the end of the loop, we decide if we execute one more instruction of this code. So we have the load, the addition, the store operation, and then the code that is used to control the end of the loop, okay? So if you think in the architecture and in these latencies that we mentioned before, you can see that we have dependencies. This instruction is loading F0, and this instruction is using F0. And at the same time, this instruction is writing a new value in F4, and this instruction is going to offload the value in F4 to a given memory address, okay? So according to these latencies, we are going to have one store here and two stores at least here, because we have to make time to wait until the results are ready, okay? So if we do nothing, we are going to have 3 stalls per iteration, And if we have thousands of iterations in a loop, then we are going to have 3,000 stalls. Okay, that's the idea. However, something that we can do almost immediately is to reorder the code. We can put this instruction in the middle of this one, so we make or we buy time for this instruction to complete the load. And this is going to eliminate one of the stalls. This is something that is called static scheduling, okay? And this can be done, and is actually done, by the compiler, okay? And this is going to help the processor to have a better performance. However, this cannot be fixed further, okay? Because obviously we don't have enough instructions to make a smart scheduling and avoid more of these stalls. So what we can do is to apply a source code optimization technique, which is called loop enrolling. Those of you that have HPC tools study loop enrolling or not? Loop enrolling is the idea that if I have this loop, I'm going to rewrite it in a way that in each iteration of the loop, I'm going to process several of them. So for instance, if the enroll factor is 4, I'm going to make a quarter of the iterations of the loop. But in each one of them, I'm going to process 4 different elements of array X. Okay? So when an enroll loop is translated into machine code, this is going to generate a bigger loop body, okay? Creating more opportunities for the compiler to reorder the instructions, okay? And being able to avoid the stalls. And actually, when you find this code and you are a compiler, you are able to generate this reorder loop body that is going to have no stalls, okay? So in practice, what does this mean? Normally, the compiler is going to do this by itself, okay, without you requiring it. But I don't know if you study in HPC tools that there are special pragmas to force a compiler to do loop enrolling. Did you study that? There are special pragmas in ICC, at least in the Intel compiler, where you can put in a loop, pragma loop enroll something and a number. Okay, if Emilio didn't explain you that, you can search for that information, and if not, you can do the enrolling yourself, because you are going to be promoting a better performance in your loop body, okay? Okay, so if we have dynamic scheduling, okay, this is just repeating the same ideas than before, but I believe that this table, this summary table, is quite good to summarize all the possibilities to implement multiple issues. So the idea of multiple issue is that you are going to issue several instructions at the same time. And this can be done dynamically by the processor, and these processors are called superscalar, okay? And in this kind of superscalar processor, we have like different levels of complexity. So static are those processors where the compiler is going to help the processor putting together independent instructions, okay? And the execution of the instructions is going to happen in order, because independent instructions are put together by the compiler itself. If you are not helped or not so helped by the compiler, then the processor needs to do so dynamically. And this is going to involve out of order execution. Okay? And another level of complexity is introduced when speculation comes into play, because this requires more hardware, more check-ins, but also creates more opportunities for the processor to improve the performance. Okay? The other alternative is to do so statically by the compiler. So this means that the compiler is going to create super instructions. So that's the source of the name, very long instruction word. The compiler examines the machine code generated by itself and create packages of 2, 3, whatever number of instructions that can be executed at the same time. One of the most famous architectures of this type is called EPIC. And EPIC was the architecture behind the Itanium processor, which was very popular in 2004, more or less. Okay? And this is very relevant because this was the processor used in the Finisterrae 1 computer. Okay? Not the Finisterrae 2, that is the one that we have today, but the previous version of the Finisterrae. And one of the consequences of having this architecture is that this processor, when you use GCC is an open source compiler, it's not a property of Intel, so obviously they saw that this was an EPIC processor and they tried to do their best, okay, but not so much because they were not paid directly, at least by Intel. But when you use ICC, as this is the processor from Intel, and they knew what they had to do to create these super instructions, okay, it performed much better with GCC, okay? So this is something that was well known when we used years ago the Finisterrae 1, that you always have to compile with ICC, because ICC, the Intel compiler, was more effective exploiting the characteristics of this architecture, because in this architecture was crucial that the compiler create these very long instructions, putting together instructions that can be executed at the same time. Okay, any questions so far? Okay, so as we are talking about many things in this part of chapter 2, I create this mind map, okay, just to order the ideas, okay? So we are talking in general about parallelism inside the chip, okay? So there are two facets of this: instruction level parallelism and thread level parallelism. We have covered this first half, instruction level parallelism, and we found that there were two ways to improve this kind of parallelism. One is pretty obvious, is to create deeper pipelines with more stages. Okay, so we mentioned that current pipelines have like between 15 and 20 stages. And the other, that is the one that we have commented more in detail, is called multiple issue. The idea of multiple issue is that we can start the execution of several instructions at the same time in the same cycle. In order to promote this, the packages of instructions that can be executed together can be composed statically by the compiler at compile time. And this is the case of belief instructions, very long instruction word processors, and the EPIC architecture executed together can be composed statically by the compiler at compile time. And this is the case of belief instructions, very long instruction word processors, and the EPIC architecture, that is the one in which was based the Itanium of the Finisterrae 1 version. And the dynamically scheduled the creation of this package of independent instruction is up to the processor itself, okay? And this is available in what they are called superscalar processors. And superscalar processors are most modern processors that we have in the market. Okay, so now we are going to talk about this second aspect of parallelism inside the chip, and is the concept of multithreading. Okay, so when you are in a computer, okay, for instance, in this computer, if I execute, well, I don't have the stop, but I have top command, you are going to see like several processes executing at the same time. And I believe that in top, they don't group by threads, okay? But what you have here are also, besides processes, like some of the programs have several threads executing at the same time, okay? So anybody knows the difference between a processor and a thread? Because apparently they are the same, no? We can create like several instances of the same program. Can anybody give me a quick definition of a thread? What is a thread compared to a process? One process can execute like several threads. For instance, when you are using OpenMP, you are creating several threads of your program to collaborate doing something, okay, some task. So normally, threads are defined like lighter version of processes where you can switch the context more easily, okay? This is going to be more or less the most straightforward definition. Okay, so just to illustrate this and the potential benefits of this, I have two processes or two threads, okay? And then this is A and this is B. And as you can see, at some point in A and at some point in B, I'm going to have some stalls, for instance, because I'm loading information from memory. And as you know, when you have to load something that is not in the cache, you have to go to the main memory. For instance, it's going to take you, I don't know, 100 cycles of the processor. And this is a long time. It's not even a second, okay? But for the processor, this is a long time. So the intuitive idea of this is that while thread A is waiting for the memory, why don't I start the execution of instructions of another thread, B, okay? And obviously, and as you can see in this very simple example, this approach saves time, okay? Something that has to be taken into account is that if we measure the execution time of A1 and A2, and B1 and B2, and we compare it with this A1 and A2 and this B1 and B2, the execution of one of these tasks in linear time takes more time, okay? Because when you use threads, you have usually some context switching and you have to pay for it. But at the end, you are promoting a better utilization of the resources of your computer, okay? Okay, so this is the basic idea. The idea of multi-threading in general is that you are going to have several threads running at the same time and sharing, and this is a key factor, sharing processor resources, okay? So obviously, the processor has to keep somehow the state of each thread, okay? Because for instance, the register file, you know what the register file is? It's the place, the piece of hardware where the values of the different registers is stored, okay? So obviously, if you change from one thread to the other, the value of register F0, for instance, can be different, okay? So this is part of the state of the processor associated to a thread. Also, you have to keep separated program counters. Program counter is a special register where you store the address of the next instruction to be executed. So obviously, you are executing several instances of the same program or different programs, okay? So you don't have to be at the same point, or the next instruction to be executed don't have to be the same. And also related to virtual memory, you are going to have separate page tables to translate virtual addresses into physical ones per thread, okay? The shared memory, for instance, the main memory is already ready to support multiple processes. Actually, when we talk about the virtual memory mechanism, we thought that one of the reasons to adopt this and why this is implemented in every computer is that it supports multiprocessing, and in this case, multi-threading, in a transparent manner for the programmer, okay? And obviously, this is going to be key for the performance of threading. It's very important that we have hardware that allows switch between different threads very rapidly, okay, very fast. So the first question that we are going to answer, and this is an important question, and this is the reason why I included in my mind map, okay, is when to switch. So as always, we have like a degree, okay, a gradation, and in one edge, we have fine-grained switching. So this means that we switch the thread every cycle. So if we are executing two threads in a core, in a processor, the first cycle, I execute one stage of one instruction of one thread, and then the next cycle, I change completely. I execute one cycle or one stage of one instruction of a different thread. Okay, this doesn't seem like very, how would I say, very efficient, okay, because you are switching all the time, and you know that you have to pay for switching. In the other edge of the gradation, we have what is called coarse grain. And we only switch the thread, in this case, when there is a long stall. Like, for instance, when you miss the cache. When you are loading something from memory, you go into the memory hierarchy, and you don't find the data on the cache. You have to go to main memory. You know that this is going to take time. So you can switch the thread. When you execute several threads, yes.
Because maybe another thread will another hit.
No, because the memory access can work independently from the processor. So you can be doing the memory access in parallel and continue the execution of another instruction in the processor. Okay, that's the idea. When you have several threads executing at the same time, you need replicator registers, program counter, etc. Okay, we already mentioned this. And then difference between fine-grained multithreading and coarse-grained. In fine-grained, you switch every cycle. So basically, what you achieve is that you interleave the execution of instructions from different threads. And still, if one of the threads stalls, you are not going to be switching to an stalled thread. Okay, you are going to be smart and use that time to progress in the other thread. In coarse-grained multithreading, only switch when you know that there is a long stop, and the example is when you miss the cache, when the data is not in the cache, and this is going to simplify the hardware, okay? But the problem is that when you have short stalls, like a data hazard, one instruction generates a piece of data and the other consumes that piece of data almost immediately, these kind of stalls are not going to be hidden when you use coarse-grained multithreading. When you have, well, this is the relationship of the previous idea of having multiple issue dynamically scheduled processors together with several threads being executed at the same time. The idea is that when you have several threads, the candidates to be issued at the same time don't have to be just instructions of a single thread. You can take instructions of different threads. Okay, and obviously, this is a big opportunity to improve your performance. The first example of this was a mechanism that is still available in Intel, and that was called hyperthreading. And the Pentium 4 was the first to have this and was able to execute two threads at the same time. Okay, so this is a graphical representation of the idea of simultaneous multithreading. Okay, in simultaneous multithreading, what you are going to do is to issue concurrently instructions from different threads, not from the same threads. That is what we were doing at the beginning of today's class, but also from different threads. So this is the situation that we had 20 minutes ago, okay? This is time in the processor. Time in the processor is measured in cycles, and these are the resources that are available in the processor, okay? Every column is a different resource, and this is the legend. Okay, so what you can see is that in the first cycle, I execute two instructions, and they occupy two different resources, okay? In the next cycle, I occupy or I use three different resources, and so on, okay? However, when I do simultaneous multithreading, I have a better situation, because in addition to scheduling instructions of one of the threads, I introduce in the pipeline simultaneously instructions of a second thread. And this implies a better resource utilization, right? Okay, and I believe, all of the three architectures that I linked in the chat use this, okay, or have some of these capabilities. Okay, so in hardware, what do we need? What we need is several program counters, not so many as they are represented here, okay, but several program counters, one per thread. Then you can fetch one instruction with per program counter, and then you need register renaming. Remember that register renaming was used aggressively by the compiler in order to avoid some data hazards. Okay, so you need these units replicated. Normally, you need to replicate the register file, both to read information from there, different versions of the information from there, and to write the results at the end of the computation. And maybe, because you can say, okay, at the end, I'm replicating the full pipeline. Okay, and if you replicate the whole pipeline, you are just replicating the core of the processor, and this is a multi-core. No, some of the resources can be shared between different threads. Okay, because if your scheduler is smart, it's going to put a division of one thread together with a multiplication of another thread. Okay, but not obviously with another division of another thread, because if that happens and this unit is not replicated, then you are going to have a problem. Actually, this is a trade-off. Normally, those resources that are cheap, like integer arithmetic logic units, are not replicated. No, the opposite, are replicated, okay, because they are cheap. But the costly unit, like the floating point units, sometimes they are not replicated. So it's up to the scheduler to avoid these structural hazards. Okay? Okay, so this figure is very similar to the one that I showed you 2 slides ago, but this summarizes the situation. Okay? This is time. These are resources. Okay, and in this case, we have just abstract resources. And these are different situations. In a superscalar processor, by definition, we should only have one thread running. Okay, this doesn't mean that the reference processors that I linked in the chat are just like that, because actually they are like this. Okay, the more evolved version of a superscalar. But in superscalar, you are issuing several instructions of the same thread, okay, in order to make a good occupation of the hardware or a good utilization of the hardware. If you use multi-threading, you have like 2 different approaches. Fine-grained is that every cycle you switch the thread, and you can see that clearly represented here. Okay, and in coarse-grained, okay, this is in Spanish. I don't know why it's not translated. This is coarse fine-grained, and this is coarse-grained. Okay, and in coarse-grained, what you do is that you execute a thread until it stalls, because there is a costly memory access. And then you put cycles of another thread, and so on. Okay? And you are switching threads all the time. But in simultaneous multithreading, you have a much more complex situation, because at the same time, on one dimension, you are issuing instructions of different threads. Okay, so in the same horizontal axis, you can see instructions from different threads being executed at the same time, and obviously this creates the best possible hardware utilization. Okay, and this is just another idea, and is multiprocessing. In multiprocessing, what you have are instructions of different threads being executed by an absolutely disjunct hardware. Okay, so this means that this is not the same hardware at all. You have like everything replicated, because if not, that would not be possible. Okay, so yes.
For 2 and 3, that's the point of having multi-thread.
This one and this one? No?
2 and 3.
2, yes, and 3.
No, not the thread, the diagram.
But in which column? In?
If you know it goes. I don't see the point of having multi-threads if you don't execute at the same time.
But you are meaning this column, in simultaneous multithreading.
The one before.
This one?
Yes.
Okay. Here, you are executing several instructions. You have multiple issues. So you are starting several instructions of the same thread at the same time. At this point, there must be a stall, because there is a costly memory access. So you start, yes, I don't know why it happens this. You are meaning this?
Yes.
Yes, I don't know what is happening here. No, because there is not a pattern for this. It must not be a thread. I don't know what is happening there. This must be just a misrepresentation. Okay? Because I don't see the point of this. Yes? Okay, so when you did you test any of your OpenMP programs in Finisterrae 2? Yes. How many threads did you create? How many?
8.
Only 8? Why?
Small programs, so we don't really.
Ah, okay. Okay, if you use a larger problem, you have to be aware that in each node of Finisterrae, you have 24 physical cores, 2 processors with 12 cores per processor. That's a total of 24. But you can give a try to use 48 because it has simultaneous multithreading. Actually, you can use 96 or whatever, okay, and it's not going to break. But between 24 and 48, sometimes you are going to get a smaller performance gain, okay, because the use of simultaneous multithreading. Okay, so when you have a heavy program to implement, you can try that. And actually, probably your teacher of OpenMP is going to ask you that, okay, because it's a good test to do. It doesn't, I made the test this morning with a matrix multiplication with a parallel 4, okay? I believe that the time with 24 was 0.18 and with 48 was 0.18. It's not a big deal, okay? Because it's not so effective for OpenMP for multi-threading programs. Okay, so other approaches to multi-threading. Okay, one idea is not Google. Doesn't sound like Google. Okay, so another idea is chip multiprocessor, also known as CMP. The idea is that you are not going to share anything in the core. You are going to just have several copies of the same core on the same on a die. Okay, maybe you can connect the cores at the level 2 cache level, and one example of this is the IBM Power 4. Okay, this is quite old architecture. Actually, in the state-of-the-art architecture, I put you the Power 9, that is from 2019, and I believe that now they are already selling the Power 10. Okay, so the Power 4 is like a very old architecture, maybe from 10 or to 15 years ago. So in this case, the benefits is that the replication is simpler. Okay, you just copy the same core over and over, so you can put more hardware in the same density, and you can lower the latency between the processor. The problem is that you are going to trade off a single thread performance. An evolution of this idea is that you are going to have a CNT, but with multi-threading added at the core level. Okay, so when you have several threads at the same level, the idea is that they are going to share expensive results, like I mentioned before, the floating point unit. The floating point unit is something that is very costly in terms of the amount of transistors or amount of area that is required for the implementation, and it's something that you can share inside a core. Also, they can share the level 2 cache. This is the idea behind an architecture that is called Niagara, and there are several versions of the Niagara architecture, and one of the most famous processors of this type are from Sun, the UltraSparse T1. Okay, it's not popular for desktop computers, but just for supercomputers or servers. The benefit of this, beyond the benefits that were already mentioned for CMP, is that as they also share the costly units like the floating point unit, so you have a better utilization of the resources. The problem is that if you share the floating point unit, there is a harm or a risk that this becomes a bottleneck when you enter in an area of the code where you have many times in a short period the floating point unit that is shared. And actually, in the second generation of this architecture, Niagara 2, they don't share the floating point unit. Okay? Okay, so this is like it happened in the case of instruction level parallelism, a summary table for different multi-threading approaches. So we have no multi-threading, fine-grained and coarse-grained, simultaneous multi-threading, and these more exotic approaches of CNT and CMP. In this column, you find an indication of which resources are shared between different threads, and in the third column, which is the context switch mechanism. Okay, so these are just a few examples of processors. This is the pipeline of Power 4. It's not very relevant, okay? But the relevant is the evolution between the Power 4 and the Power 5. The Power 4 actually was one of the examples that we gave of CMP, okay? So we have in Power 4 this simple cores that doesn't allows the simultaneous execution of several threads at the same time. And in Power 5, one of the novelties that was introduced is that it allows the execution of several threads at the same time. And in order to do so, here you can find highlighted which pieces of hardware are replicated. The fetching and decoding mechanisms have to be replicated to have separated data path for different instructions, in the case 2, and also when you do the commit, you have to be able to make the commit of 2 different instructions concurrently. And that's the most important difference between the two architectures. Okay, one is an evolution of the other that just introduced the possibility of multi-threading. Okay, so this is a deeper detail of the simultaneous multi-threading IBM Power 5 architecture. And actually, something that you are going to find is that in this kind of architectures, they usually allow to execute 2 threads or a maximum of 4 at the same time, okay? And actually 2 is like a magic number, it's very common. So the question is, why don't you allow to execute more threads, okay? Because this is going to give you more opportunities. And obviously this number, 2, 4, or whatever, is obtained by experimentation. They discovered that, for instance, in this architecture, in this specific architecture, if they allow 4 threads at the same time, some shared resources, like the registers, cache, memory bandwidth, could become a bottleneck, okay? So just they infer it from experimentation. Okay, so the example that we gave about CMP plus multithreading, that's the idea, is Sun Niagara. That is a very famous architecture, at least between computer architects. Okay. In this architecture, what you have is one single in-order pipeline, okay, that use fine-grained thread switching. Do you remember what was this? That you switch every cycle, okay? So this idea that for all of us was crazy, of switching every cycle from one thread to another, is implemented actually in this architecture. In this architecture, we have 8 cores, and each core is able to execute 4 threads at the same time, okay? So this means that if you have 4 threads running, first cycle goes for the first thread, second cycle to the second thread, third for the third, fourth for the fourth, and start over, okay? And over. So this is the way it is implemented. Okay, so the idea, this is an illustration that is given just to show you the goodness of the idea of Niagara. This is what it happens in a core. They are representing that for each thread, you are going to have moments where you are computing in the processor and other moments where you are accessing to the memory. So you have like stalls due to memory access, okay? But if you divide this vertically, you are going to find that with this, yes?
In this case, you have only one processor.
Yes, this is one core of Niagara. This is what it happens in the whole architecture, okay? Is the next slide. But in this slide, what they are trying to show you is that at the end, if you divide this vertically, the CPU is always computing. The core is always computing something from one thread or another, okay? And is very effective at hiding the memory latencies. One potential problem of this is that if you divide this vertically, this thread is computing, but the other 3 are accessing to memory. So this kind of architecture is putting a lot of pressure on the memory system. And this is one of the main problems of this system. Moreover, if you think in the whole system for 8 cores running 4 threads each, they are running a total of 32 threads. If you check this vertically, this can put a lot of pressure, for instance, in the main memory. okay? Because at the end, the main memory is shared among all the cores and all the threads. So at some point, you have to be very unlucky and to have a lot of pressure on the memory system, okay? Okay, this is the power 6. Well, we have the power 6, that is an evolution of power 5, just to see how the power 5 evolved from power 4, power 5, power 6, and this will be power 7, okay? And you can see that the evolution is that you put an increasing number of cores, that normally the level 1 that is not represented here and the level 2 caches are private to each core, and then the level 3 is the point of interconnection between the cores because it's shared among all the threads, okay? And actually, if you go to the links that I gave you, you can see the power 9, okay? That is one of the most recent versions of the power architecture. Okay, so what we have left after the break is to talk about multi-core architectures, okay? But we are going to have like a very long break, okay, until 6:30, because you are going to have time to have a rest, okay, a long rest. But also, I would like that you consulted these 3 links, not all of it because it's very long, okay, and you try to identify the ideas that we have seen so far in HP high performance architecture subject in these architectures, okay? Because actually this is something that you have to do in your task, okay, for high performance architecture. You have to take the processor of your supercomputer, the one that you adopt, okay, and then you have to see which is the processor in which is based, and you have to go, for instance, to Wikichip and identify if it is superscalar, if it is UBELIF, if it has simultaneous multithreading, and so on. This is the kind of analysis that I want you to do, okay? If you want to do it with any of the architectures of these 3 links, it's okay. If not, just use the architecture of the supercomputer that you pick, okay? Any questions? Okay, so let's come back at 6:30.